All right, here we're asked to find the volume of the solid obtained by rotating the region bounded by y equals x, y equals 0, x equals 2, and x equals 4. About the vertical line, x equals -1. The very first thing we should probably do here is graph this situation. And what we want to do is, and again, we want to bound that below by y equals 0. So really the region that we're concerned with is that trapezoid that you see right here. And we want to rotate that about the line x equals -1. So I'm going to go ahead and draw that in, x equals -1 here. And I will do a dashed version. So let's just pretend that's about -1. That looks about -1 to me. And we want to rotate that around. Now, the very first thing we're going to do is actually draw in an approximating rectangle. Some people draw the actual three-dimensional object here, but I think it's more beneficial for me, because I'm a terrible artist, to go ahead and draw the approximating rectangle first. And let me just be forthright with you and let you know that I am going to choose horizontal slices for this, because I am doing this lecture for my students who have not learned the cylindrical shells method. Although, if you have learned cylindrical shells, you should be doing vertical slices here. But for now, let's pretend all you know is the disc and washer method, or what I call the plate method, because you're just stacking a bunch of plates. If that's the case, and I want to rotate about this line x equals -1, I'll do horizontal slices, and let me go ahead in red here and draw in one such approximating rectangle. So this guy right here is a good approximating rectangle. I can shade that in if I wanted to showcase that this is the guy that's going to be rotated around. Now you also notice that the left-hand side of this is going to change at some point once it gets up high enough to touch that y equals x box. If that's the case, then you have a new style of approximating rectangle, this guy right here. So you have two possible approximating rectangles, because the left-hand side will change. The left boundary of your approximating rectangles will change at some point. So you know there are going to be two integrals. So I will go ahead and make that note right now that I will have two integrals. So from y equals 0 all the way up to y equals this height, and you can see that this height right here, since this is the line y equals x, and this x value here is 2, then that y value must be 2. So from y equals 0 to 2, we'll have an integral 1. And from y equals 2 all the way up to y equals 4, and I know this is not technically to scale, we'll have a second integral, because again, our left-hand side is changing. Now, like I said, I am a terrible artist, and so I have tried to draw things like these for years, and I'm just no good at it, to drawing them exactly. But I'm going to give an attempt by hand here just to showcase what I think this should look like. And then, just so I don't sully this specific graph, I'm going to draw a separate graph to do this, and then hopefully come back in a second and showcase it. That is my terrible rendition by hand of what this would look like. And I actually have a better rendition that I could probably give you right now using a program called WinPlot, and a little bit of WinPlot magic. Let me bring that up. Okay, so there's our original rectangle, and so let's go ahead and just fast forward on this, and you can see this will open up. In fact, let me just grab this, and that's what the object would look like as it rotates around. That's actually a much better drawing than I could possibly do by hand. And you can see there's that open section within it, so it is a hollowed out or bored out volume, as I would call it in class. A typical plate would look like something like that. And you should notice that any of these typical plates, if you look at them top down, they sort of look like, and I'll just scoot this over so that we can really take a look, and I'm going to use a different pen color here, so let me just get all set up. Oops. Top down, you'll have this outer plate, and then you're cutting out this inner plate. So let me go ahead and draw that inner plate. And I didn't do it in the right color, but it doesn't really matter. Okay, so top down, it looks something like that. So you have this outer radius, and you have this inner radius. Radius inner. I'll put a capital I for inner radius there. So really what you're going to be doing to find the surface area of this plate is you're going to find the surface area of the larger plate first and subtract off. So you're going to find the surface area of this blue shaded plate plus the interior. Okay. And then you're going to subtract off the area of the interior. That's the idea. So area of the entire plate and then subtract out the area of the middle. And that would give you this surface area of this plate right here, which has a width in our picture. If you think about it in terms of an XY axis, that width there would be a delta Y. So it has a width, and then you have a surface area, and the surface area of this plate, again, is just going to be the total area of the plate if there was no hole. So that's pi r sub outer squared. And then losing the surface area had you cut the center hole out. So in other words, pi r sub inner squared. So you're losing that inner radius, or that inner area. Okay, and that'll be actually the whole method behind our madness. Now notice I don't really state anything about x's and y's yet, because I want us to kind of just constantly remember it's just a circle, pi r squared, and you're cutting out a central circle, pi r squared, but a smaller r in that case. And so the volume of this ith slice, and I'll use lowercase I there, so it's fairly typical. The volume in the ith slice is going to be surface area times its width. So that's going to be pi r outer squared minus pi r inner squared times its width, delta y. Now, of course, this is only supposed to be in terms of x's or y's, but not both. And in this case, it's not even in terms of x's and y's only, it has r's in it. So we have to figure out what these radii are in terms of y, actually. So here we have the shape that's going to be cut out, and the radius, outer and inner radii, are always going to be measured from the central axis of rotation. That's super important for you to remember, that you have the central axis of rotation, and that you need to measure your distances from there, or in other words, your radii from there. There's really one formula for to compute a radius, but most people think of it as two, because if you're doing horizontal slices like we are doing here, and let's go ahead and find like this guy right here, it's a horizontal slice, then really your center, your distance from center is measured along a horizontal axis. You're measuring that red distance there. What is that outer radius? And what is the inner radius? That's really what you're asking yourself. So when the axis of rotation creates a horizontal slice, then we have the following. We measure the radius using the idea of right minus left. Now, radius is supposed to be positive, and if you think about a number line, a number to the right on a number line, like 5, minus the number to the left, which would be 1, for example, gives you a positive value. Even if it was 5 minus a negative 1, it still gives you a positive value and the appropriate distance, actually. 5 minus a negative 1 is a 6. So right minus left is what you should be thinking when you have horizontal slices. If you have vertical slices, it's just top minus bottom. And that should make sense. So let's go ahead and take a look at, in both of our integrals here that we're going to deal with, what is right minus left for our radii? So again, going back to the formula for the volume, now I'm going to go ahead and concentrate right now on our first integral. So if I scroll up here, we said we have two integrals. One integral is going to be for the region that is bordered on the left by x equals 2 and bordered on the right by x equals 4. And that'll present us with our first integral. Technically, you don't actually need an integral for this, but I'm going to be somewhat lengthy with this computation just to keep it rigorous enough or general enough for any style of problem. So anyway, we are going to go ahead and have an integral for that, and the portion that we're going to do is basically the barrel portion, this piece right here, that barrel portion, or if you look at this, it's the portion here, right? That block that gets rotated around, that's what we're worried about, okay? The outer radius of that block, okay, for this first one, and I'm going to go ahead and erase those black lines there. The outer radius are outer, and the inner radius are inner. Here, and I was going to do a capital I on that. Let's see, the outer radius. Remember, it's measured from the center axis of rotation. So the outer radius here is going to be, well, remember, the x value there is supposed to be 4. So it's going to be 4, which is the rightmost x value, minus the center of the axis of rotation, which is a -1. And the inner radius will be, again, the x value at this edge right here minus the x value at this edge right there. So it'll be 2 minus a -1. So the outer radius is going to be 5. The inner radius is going to be 3. That should make sense. If you're rotating about x equals -1 and your outer edge is at 4, you actually have a radius of 5 because that -1 gives you an extra 1 there. So outer radius 5, inner radius 3. Let's go ahead and plug that into our formula. So this is for the first integral, integral 1. We get that the ith slice is going to be, I'm going to factor a pi out of those if you don't mind. Pi times the outer radius was 5, so this will be 25. Minus the inner radius was going to be 3, so this is going to be 9. Times delta y, or in other words, 16 pi delta y. That's the volume of any given slice in that first set of blocks, right? So this first region, any slice I do there that I want to rotate around, any of the slices has volume 16 pi times the delta y size. Okay. Now let's go ahead and worry about the second integral. Remember, integral 2, and I haven't even done the integration yet, okay? But the second integral is concerned with the region starting at y equals 2 and ending at y equals 4. And notice in this case, the left edge is defined by y equals x, and the right edge is defined by x equals 4. So the left is defined by y equals x, and the right is defined by x equals 4. In the rotation, let me go ahead and scroll to it, and I'll erase all this again. Don't need it. Okay. In the rotation here that we have going on, we have, and let me finish out this is kind of bothering me. Okay. We have a left edge. Remember, we're rotating this piece now. Okay. We have a left edge that's at x equals 4. That's what the left edge is. And a right edge for that slice. I'm sorry, that was supposed to be, I was supposed to say the right edge. The right edge is x equals 4. The left edge is y equals x. So let's go ahead and take a look at this and actually write this in. So the outer radius of this rotation, the outer radius defined by this edge right here that I'm really making black, okay? The outer radius is equal to the rightmost x value minus the leftmost x value, or in other words, where the rotation is happening. So minus a -1. Okay, that's what the outer radius of this rotation is. So we're going to take this guy and rotate it all the way around, and the radius of that is this distance. Okay. Then the inner radius is going to be, again, whatever the x value is at this random point that I'm highlighting right here, minus the center. So it's the x value at that random point. It's no longer x equals 4. It's a random x value between 2 and 4, right? Because this is x equals 2 and that's x equals 4. So it's some random x value between 2 and 4. So all I can say is that this is going to be some x value. I'll call it x sub I because it's the ith slice and it kind of works that way. And remember, it's the rightmost part of this rotating. So it's the rightmost value, which is x sub I, minus the center, which is just a -1. And so the inner radius is going to be x sub I plus 1. So let's go ahead and plug these into the formula. And again, if you're wondering about that, it's the outer radius is this distance and the inner radius is this distance. The outer radius obviously is 4 minus a -1. The inner radius is whatever this x value is minus a -1. And we don't know the x value, so it's called x sub I. So again, factoring the pi out of these two, I just go ahead and do that. The outer radius we said was 5, so let's call that a 25 when we square it, minus. And the inner radius was going to be an x plus 1, x sub I, plus 1, quantity squared, and a delta y. Now this is no good. This is kind of illegal. What we need to do is change x's somehow into y's, and luckily we know we have a strong relationship between x and y because x is equal to y. That was the equation we were given. If that was instead the graph of y equals x squared, I would not trade out x for y. I would trade out x for the square root of y. Okay, so in this case, this is the same thing as saying pi times 25 minus the quantity y sub I plus 1 quantity squared delta y. Now I have everything set up. These are my two equations that I'm going to plug in to my integral. And we just have to worry about the limits on our integral. The true volume is going to start at, let's see, the first integral was concerned with y going from a height of 1. And we're going to stack those plates until we got to y equals 2. Let's just double check that. We start stacking the plates at y equals 0 and going all the way to y equals 2 here. Okay. And then once we're done stacking those, or obviously we have to throw on their volumes. It's 16 pi dy for those plates. And once we're done with those, we start stacking plates at 2 and going to 4, finishing off the stacking. But these plates are all going to be of volume pi, which I'm going to factor it out, times the quantity 25 minus quantity y plus 1 squared and quantity dy. And from this point forward, it's an integration problem. All we have to do is integrate this stuff to figure out what the true volume is. So this is a pretty complex problem. 16 pi y is what the antiderivative of 16 pi is, and evaluated from 0 to 2. And then this will be plus 25 pi y, evaluated from 2 to 4. And minus, this will be pi y plus 1 cubed over 3, evaluated from 2 to 4. And if you do the computations here from this point forward, it's just ... computations, and I think this comes out to be 148 thirds pi. That's what it comes out to be. I could be wrong about that, but I don't think I am. So again, to reiterate, the whole problem started with us wanting to rotate about a vertical line that was not the y-axis. And so that created an interesting type of radius situation. These are more common. These are actually very common. And so when you're asked to rotate about something other than an axis like X or Y, you have to start thinking about, well, what are my actual radii? So for vertical, if you're rotating them on a vertical non-axis, then your radius, you can compute radii by right minus left. If it's a horizontal rotation, let's say around y equals -5 or something like that, the radii are going to be top minus bottom. Okay? Always. There's no exception to that. Okay, I think that this is done.